Chapter 10, problem 61. A long uniform road of length L and mass M is pivoted about a horizontal frictionless pin through one end, as you can see in the figure below. So here is the road, and this is the pivot in one of its ends. The road is released from rest in a vertical position, as you can see in here. So it was along the y-axis, and then it was released from rest. At the instant the road is horizontal, so along the x-axis, you have to find A, its angular speed, B, the magnitude of its angular acceleration. So you have to find omega, then you have to find alpha. And in part C, the x and y components of the acceleration of its center of mass. And in the last section, you have to find the components of the reaction force at the pivot, how it is. So we have to find omega, alpha, ax, ay of the center of mass, as well as the components of the reaction force Rx and Ry. So this is the road in its original position, in the vertical position, and it was released from this vertical position. Then it was at the time when it was horizontal, in this horizontal position. The question is in the first part of this question, how much is omega, the angular speed of the road? Angular speed, omega. So of course, one of the possible ways to solve this problem is to apply Newton's second law on the rotational motion of this road. However, this doesn't sound to be the most prominent method because actually in this case, we have two states, or we have two configurations in which the road is. The first one is the vertical position, and the last one is the horizontal position. And the initial configuration, it was released from rest, so we have kinetic energy equal to 0. And in the final position, we have kinetic energy different than 0. And we have a difference in the gravitational potential energy between the initial state and the final state. So since it is the case, it seems quite reasonable to apply the conservation of mechanical energy of the road to conclude or to determine the angular speed. However, we should make sure at the beginning that we have conservation of the mechanical energy. So if we consider the system made by the road and the pivot and the earth, this system is isolated, and the mechanical energy of this system is conserved, because actually only conservative forces acting within the system. So this is why we can apply conservation of mechanical energy. So we can write down that only conservative forces they act within the system, the system that consists of the road plus the earth. And of course, the pivot is part of this of the road. And so we can write down that we have conservation of mechanical energy. Delta EM is equal to 0, which means that mechanical energy in the initial state is equal to the mechanical energy in the final state. And so we can write down K initial plus U initial is equal to K final plus U final. In the initial state, we have 0 kinetic energy because the road was released from rest. And we can also say that in the final state, we can take the level of the road to be our reference for the gravitational potential energy. So we can write down that in the initial state, in the final state, the gravitational potential energy is equal to 0 as taken to be the reference. And so we end up with, in the initial state, we have a gravitational potential energy given by m times g times y of the center of mass. And the center of mass was L over 2. So here is the center of mass. It's given by, center of mass is given by the middle point of the road, and it was at distance L over 2 from the level, the reference level for the GPE. So we multiplied by L over 2. In the final state, لما كانت الroad in the horizontal position, it has a kinetic energy which is due to the rotational motion. وبالتالي this kinetic energy is given by half I omega squared. This is it. So given now we need to apply we need to determine what is I لأنه هذه هي الunknown الوحيد اللي صار عندنا إياه. If we already can reduce the half in both equations, so we end up with m times g times L is equal to, here the moment of inertia that we need to apply هو the moment of inertia of a road with respect to the axis passing through one end. اللي هو it's defined or given by 1/3 times m times the length squared multiplied by omega squared. And so now if we again reduce the factors m and then L on both sides, then we can immediately deduce that omega squared is equal to 3 times g divided by L. And so we end up, or we can deduce finally that omega is equal to square root of 3 times g divided by L. And this is the answer we are looking for. So this is omega. This was about part A. So we end up with the angular speed given by square root of 3g divided by L. Now, in part B, it is asking about the magnitude of its angular acceleration. So how much is the angular acceleration alpha? This is the question. Part B, the question is how much is alpha? Okay. In this case in here, we know how much is omega in the horizontal position. But actually, we cannot apply the kinematic equations that we have seen in the course. So we cannot conclude what is alpha based on the value of the omega in the final state or in the in this horizontal position. Instead, we need to determine alpha by applying the Newton's second law, right? And if you apply Newton's second law and its horizontal position, so in its horizontal position, only the gravitational force has a torque that is different than zero as a force acting on the road. So we can write down there for tau net, which is the summation of all the torques exerted on this road, is equal to I multiplied by alpha. So we can keep the vector or we can move it. The point is that in the vertical position, only the gravitational force has a non-zero torque. So this tau is nothing else than the torque of the gravitational force. So if you just have a look, this is the road. At this, in this horizontal position, this is mg. It's acting on the road at its center. And the distance between the axis of rotation and the gravitational force is given by L/2. And also the point of application of this force is, so the vector R in this case is perpendicular to mg with R equals L/2. So we can write down m times g times L/2 as the lever arm or the perpendicular distance between the axis of rotation and the point of application of the mg force is equal to 1/3 times ml squared multiplied by alpha, right? So note that I is equal 1/3 ml squared because the road is rotating with respect to the axis passing through one end. We can already reduce the mass term, and then we can use one of the length terms in the right-hand side of the equation. And so here we can finally deduce that alpha is equal to 3 multiplied by g divided by 2 multiplied by L. And so this is the expression for the angular acceleration alpha. So that was the second question. Now, the third question is, you have to determine at the instant the road is horizontal, the x and y components of the acceleration of its center of mass, right? So let's write down, or let's at least try to guess what are these components, and let's draw a figure for this purpose. So in this horizontal position, if we're looking at the center of mass in here, the point, the dot point, the dot black point, if you want to draw the acceleration, the components of the acceleration, so we know that this point is moving along a circle as long as this road is rotating, right? And this circle has the center as the axis of rotation, which is passing through the end of the road. And so we know that at any time, this point is traveling, which is the point of center of mass, It's traveling along this circle. So it has, when going down, when the road is going down, this point has the acceleration a. I would call it for the moment a radial. It's pointing all the time towards the center of the circle. It's given by this point in here, with axis of rotation. And since it's going downward, so the speed is increasing. And so therefore we expect that at this point here, we have a tangential acceleration that is pointing downward. Now, in this question, we are asked to determine the x and the y components of the acceleration vector of the center of mass. So how much is ax and how much is ay? Now, if we take, let's take first of all x and y in this direction. So let's take conventionally, or as it's written actually on the figure. So x to the left and y upward. So in this case, we can guess how much is ax and ay by simply projecting r and at along the x and the y axis. And so we can deduce the following. So ax is nothing else than, it's minus ar, because ar is along the x-axis but in the opposite direction. So it's minus ar, and ar is nothing else than v squared over r, right? Or it can be written as r times omega squared, actually. So both are fine. And so let's write it down as minus r multiplied by omega squared, because we have the value of omega. So how much is r? This point, the center of mass point, is at distance L over 2 from the axis of rotation. So it's equal to minus r هي L over 2, والomega squared هي عبارة عن 3g divided by L, as we can see. So 3g divided by L. And now if we just cancel out the L, we end up with ax equals minus 3g divided by 2. This is the value of ax. And now if we have ay is equal to minus at, because the only vector, acceleration vector along the y-axis here is a tangential, and it's pointing downward. So we expect ay then is equal to minus at, so it's equal to minus r multiplied by alpha, minus r alpha. So again, r is given by L over 2, and alpha we have just derived it earlier is 3g divided by 2L. And so this is equal to minus 3g divided by 4, where L cancel out between the numerator and the denominator. And so we end up with these two values for ax and ay, given by minus 3g over 2 for ax and minus 3g over 4 for ay. The last question is, you have to find the components of the reaction force at the pivot. So in this last question, part D, given that we have this road as it is, so I will draw again the figure. So here is the road, and so we have the center of mass is at this point in here. From the previous questions, we have to deduce how much is the component of the reaction force along the x-axis and along the y-axis. So the reaction force, okay, at the pivot, So actually, let's call this force, we can call it N, or we can call it R. I mean, you can call it whatever you want. So the point is that we want to see in this horizontal position, after going down from rest, how much is the vector N, right? Okay, it's not quite straightforward to see how much is N if we apply Newton's second law without knowing how much is the acceleration. However, بما انه هون احنا عم ندور على force N. Okay, so اول شيء بنفكر فيه انه the way to access a force هي بالمبدا to apply Newton's second law. بس اذا هون طبقناها من دون ما نعرف شو هي ال A ما رح نوصل لمحل. However, we know انه ال A هي equal لل AX plus AY, right? وهون نحن بنعرف already شو هن ال AX وال AY، شو هن ال components، لانه already جبناهم. فاذا بنطبق نيوتن's second law بنقول انه sum of external forces is equal to m multiplied by the acceleration. If you know the acceleration, then you can deduce what are the forces, right? And so we know already that we have two forces acting on the road in this position. احنا عندنا بنعرف انه في عندنا الام جي اللي هي الويت، وبنعرف في عندنا الان اللي هي reaction of the pivot. How this summation is equal to m times a. So this is why let's make the projection of this equation onto x and onto y. And so we end up with along x, or let's start with along y, let's start, or along x-axis, it doesn't matter, both. So along x, what do we have? Look, so this is mg, right? So this, we know how is the direction of this force. It's pointing downward. At this point in here, we know that the normal is passing somehow through the rotation axis, but we don't know how much is this force and how is the direction of this force. لسبب رح سميها nx along the x-axis. وراح أقول إنه البروجكشن mg هي 0. رح نسميها البروجكشن nx هي للn هي nx. اوكي، نحن ما بنعرف اذا البروجكشن تبعيتها بوزيتيف اور نيجاتيف. هذا الشيء رح يبين معنا من خلال الايكويشن يلي هون حتطلع معنا هي ايكوال للm times ax، رايت؟ بس بما انه اوكي here m is capital M، للرود استعملناها capital M everywhere. We should keep it capital M. m times ax، ونحن بنعرف شو هي قيمة ال ax، هي minus 3g divided by 2. So we just need to replace. We end up with nx equals minus 3 times mg over 2. And so this is the expression, or this is the x component of the normal force. Now, if we make the projection along the y-axis, what do we end up with? هلا along the y-axis تفرق شوي، لأنه نحن هون along the x-axis ما كان في عنا ولا أي force تاني، بس along the y-axis we have the mg force, right? So we can write down minus mg plus ny is equal to m multiplied by ay. And so let's put it like that. And ay is equal to minus 3g over 4. So we end up with minus 3 over 4 times m times g. From here we can deduce that. So ny is equal to minus mg لتاني جهة بتصير plus mg minus 3 over 4 times mg اللي بتطلع معنا هي 1 over 4 mg. So this is the expression of ny. And so as you can see, ny is positive, which means that إذا بدنا نجي نرسمهم لهدول ال two components على الرسمة، ال nx طلعت معنا negative، يعني ال nx it points right leftward بعكس اتجاه ال positive x axis. So this is nx. ال ny معنا طلعت positive، معناتها هي بنفس اتجاه ال y axis. So ny points upward. So this is ny, and that means that in this position, بهالposition لما تكون الهورود in its horizontal position, the vector force normal n, it's given by this vector اللي هو الvector n بهالشكل هيدا. So هيدا هو ال n vector, right? So this is it. هيدا هي normal force as it is drawn in this figure home. ونحن ما عرفنا ال nx وال ny الا من خلال الايكويشن نيوتن سكند لو. يعني احنا هون ما خمنا شيء مننا لحالنا، احنا بس عملنا بروجكشن ال nx وال ny، افترضناهم انه هن بنفس اتجاه البوزيتيف x axis والبوزيتيف y axis، بس طلع معنا من خلال نتيجه ال ax وال ay انه ال nx هي نيجاتيف وبالتالي هي بعكس اتجاه الاكس، اما ال ny طلعت معنا بوزيتيف وبالتالي هي pointing upwards. And so this is it for this problem. Chapter 10, problem 76. A uniform solid sphere of radius r is placed on the inside surface of a hemispherical ball with much larger radius r, capital R. The sphere is released from rest at an angle theta to the vertical and rolls without slipping, and as shown in this figure. You have to determine the speed, the angular speed of the sphere when it reaches the bottom of the ball. So when this sphere is at this position and then it's released from rest, it will roll inside the ball, this ball of radius capital R without slipping. And then at some point, at some time, it will arrive to this, the bottom of the ball, so to this vertical position. The question is, how much would be the angular speed of the sphere when it is at this position? So this is our figure, and what we are looking for is to determine when this sphere arrives to this position on the bottom, how much would be its angular speed omega. So how much is omega for the sphere at the position in blue, as you can see in the figure. Now let's see what happens when actually this ball is released. It's released from rest. At this position, the first position, initial position, the center of mass is defined by the center of the sphere. So the center of mass was at this position as shown in the red line. And when it comes to the bottom of the ball, the position of the center of mass becomes at this position. So practically the center of mass, it has fallen at this given distance, let's call this distance h. And so there is a variation in the gravitational potential energy of this sphere. Now, how can we determine the angular speed omega? Again, here, if we have conservation of mechanical energy, it would be great to apply the principle of conservation of mechanical energy because it's much easier to deal with this problem using the energy approach. Now, what do we have? We know that the sphere is moving inside this ball and its motion is defined by a rolling motion. So it's rolling without slipping. So since slipping does not occur, that means that the friction force between the sphere and the ball is a static friction force and does zero work. And so this is why we have conservation of mechanical energy. So let's apply the principle of conservation of mechanical energy. And of course, here we're talking about two configurations or positions for the sphere. The first one, or the initial one, let's say it is when it was in the initial position making an angle theta with the vertical, it was at rest. And let's say that the final position we're talking about is when it is at the bottom of the ball. And so we can write down the mechanical energy in the initial position or initial time is equal to the mechanical energy at T final. Now, let's put this into details. So K initial plus U initial is equal to K final plus U final. Now we have to choose some reference level for the gravitational potential energy. So let's take actually the position of the sphere, of the center of mass of the sphere, and the final at T final to be the reference level for the gravitational potential energy. And so now let's define all our variables. So initially, the sphere was released from rest. So this is why its initial kinetic energy is equal to 0. If we take the reference level for the gravitational potential energy to be at T final, that means that U final as well is equal to 0. And only we have U initial and K final as non-zero terms. So for U initial, let's put it, it's equal to the mass of the sphere multiplied by G multiplied by H, where H is the distance for the center of mass in the initial position above the reference level. So what is the kinetic energy of the sphere in the final position? Well, since the sphere is rolling without slipping, so the rolling motion, as we have seen in the lecture, it is a combined motion of a translation and a rotation. So this is why here for K final, we're going to include two terms. The first one is the translation, the kinetic energy first translation. So it's half mv center of mass squared plus for the rotational kinetic energy half I c center of mass times omega squared. So in this case, we are looking for omega, as you can see. So this is why we are going to write V center of mass in terms of omega. And since we have rolling without slipping, so this could be written as half times m times r omega squared plus half times I center of mass times omega squared, where we have used here that V center of mass equals R omega because we have rolling without slipping. Without slipping. Now we will have actually, so this is half times m r squared omega squared plus half. How much is the moment of inertia of a sphere with respect to the axis passing through its center of mass? Actually, if you just have a look at the table inside our book, you'll find that for a solid, uniform solid sphere, the moment of inertia with respect to an axis through the center of mass is given by 2 over 5 times mr squared, where m is the mass of the sphere and r is the radius of the sphere. All of this multiplied by omega squared. So we end up with mgh equals 1 over 2 plus, from the second term, we'll have 1 over 5. All of this multiplied by m times r squared times omega squared, which is a common factor. So which gives back 7 over 10 times m r squared omega squared. So m cancels out in both equations, and so we can write down omega squared as a function of r, g, and h. But still, h is not known, actually. This variable we have introduced ourselves in the problem, and it's not known. We have to define how much is this variable h. So for this reason, let me draw the sphere in both the initial position and the final position, and then write down how much is h. So have a look. السفير هون كانت هي بالاول in this position, right? نزلت على البول، هيدا هو البول عمليا spherical ball, and then صارت بهيدي الفاينل position. So نحن we are looking at the distance between this point here, when the point was over here, and between this distance in here. So نمشي من السنتر هو بهالشكل، وهون هيدا السنتر اوف ماس صار هون السنتر العالم. علما انه هي هالنقطة هالبول it is at actually at distance from the center of the ball اللي هو هون. هي it is at a distance r. radius تبع البول اللي هو عمليا distance ما بين هالنقطة والنقطة لهون تحت هي عبارة عن r. ونفس الشيء بالنسبة لتاني position. اوكي so إذا نحن بدنا نجيب هاي الديستنس اللي هي ال h اللي عم ندور عليها. Okay, we have to see how much is the distance above and below. طيب نحن بنعرف إنه من بين فوق وتحت، من بين هالنقطة وهالنقطة، هو نفسها هيدي الديستنس هي نفسها الراديوس تبع السفير. So هاي هي عمليا r small r. ونحن بنعرف إنه الديستنس كاملة من فوق لتحت هي عبارة عن r كبيرة، يعني distance من السنتر للبول لعند طرف البول هي عبارة عن r. فإذا بنطلع على الديستنس ما بين هالنقطة هون اللي هي السنتر للسفير والسنتر للبول، هيدا عبارة عن الراديوس الكبيرة r ماينس الراديوس الصغيرة، لأنه هي عبارة كلها لهون لهالنقطة هي r، ولهالنقطة اللي عندها النقطة في عندنا السمول r اللي هي radius of the sphere. So this distance اللي هي from the center of the ball to the center of the sphere it's given by small r minus r. So باقي عنا نجيب نحن هون لحتى نقدر نجيب نطلع ال h، لازم نشوف قد ايه هي هالديستنس، قد ايه هي هاي الديستنس from here to there، من نص البول لعند السنتر اوف ماس اوف ذا سفير لما كانت بوضعها الانيشال، لما كانت بوضعها البوزيشن القديمه الاول بوزيشن لها. So here it is. Okay, so how much is that? So have a look. نحن بنعرف انه هي بالمبدأ كانت at this position كان في عندها angle theta مع ال vertical, right? And so إذا بنجي بنكتب cosine theta، إذا بنجي بنكتب cosine theta، let me draw it here. So cosine theta inside this triangle اللي هو it's made of this point, so whole points in blue. نص الcircle، sorry، نص البول، هيدي النقطة والنص السفير. هول 3 نقاط بنقدر نكتب فيهم cosine theta is equal to the distance we are looking for, right? I will call it x for the moment. So let's say cosine theta is equal to adjacent x divided by hypotenuse اللي هي r minus r. So from here we can deduce that x is equal to r minus r multiplied by cosine theta. And so now actually we can very easily deduce the value of h. So h هي عبارة عن distance ما بين center of the ball لعند center of the sphere هون لما كانت بالفاينل position اللي هي r minus r. So we can deduce from here that h is equal to r minus r اللي هي من فوق من هالنقطة هاي لهالنقطة تحت minus x. Right? So it's given by r minus r minus الx نحن جبناها قبل شوي هي r minus r multiplied by cosine theta. And so we can deduce that finally h is equal to r minus r. ناخدها in common factor times 1 minus cosine theta. بما انه r small r is very negligible compared to the radius of the ball لأنه هو he said in the given انه you have a solid sphere of radius small r is placed on the inside surface of a hemispherical ball with much larger radius capital R, which means that we can actually neglect small r قدام capital R, and so this is approximately equal to capital R multiplied by 1 minus cosine theta. And so if we are back to the original equation بيطلع معنا كالتالي. نرجع للإيكويشن الأساسية اللي هي كانت MGH. So again back we end up with MGH is equal to 7 over 10 times mr squared omega squared. هي الإيكويشن اللي وصلنا لها بالأخير. So if we cancel out the factor m and we بنحط h بقيمتها بيطلع معنا إنه الأوميجا squared it's given by. So we end up with g times r minus times r times 1 minus cosine theta لأنه عملنا already approximation. g times r 1 minus cosine theta is equal to 7 over 10 r squared omega squared. And so we can now write down that omega squared is equal to 10 times g times r times 1 minus cosine theta divided by 7 times small r squared. وإذا ما نجي نطلع مباشرة الأوميجا بس ما نحط square root على هيدا الإكسبريشن. And so we end up with omega equals to 10 times r times g times 1 minus cosine theta divided by 7r squared. And so this would be the answer. So as you can see, we could determine the angular speed of this sphere by simply using the principle of conservation of mechanical energy. And we have, of course, taken into account the fact that it is a rolling without slipping. So this is why we can apply the conservation of mechanical energy. And this is why we can write down V center of mass is equal to R times omega. And of course, be careful here, V center of mass is small r multiplied by omega because the sphere is rolling. So this condition applies for the sphere. The linear speed of the center of mass of the sphere is equal to the radius of the sphere multiplied by the angular speed of the sphere. So this is it for this problem. Chapter 10, problem 85. A spool of wire of mass m and radius r is unwound under a constant force F as shown in this figure. Assuming the spool is a uniform solid cylinder that does not slip, show that the acceleration of the center of mass is equal to 4 times F over 3m, and the friction force is to the right and equal in magnitude to F over 3. In part C, if the cylinder starts from rest and rolls without slipping, what is the speed of its center of mass after it has rolled through a distance d? So as you can see here, we have this spool of wire. It's modeled as a cylinder, uniform solid cylinder. And actually this cylinder, it rolls without slipping on this flat surface under the action of a constant force F applied to it. So we have to show that the acceleration of the center of mass is equal to this value, and that the friction force acting is pointing to the right and is equal in magnitude to F over 3. So let's discuss this problem on the whiteboard. Okay, so in this problem, we have to show these, we have these three questions. And so we have to show that A is equal to 4F over 3M, that the friction force is equal to F over 3, and we have to determine the expression for the speed of the center of mass. Now, هو قالكم شو هي الفريكشن بأي اتجاه لازم تطلع معكم. بس نحن رح نعمل اناليزس لحتى نقدر نفهم كيف الفريكشن بنحددها وليش بالاتجاه اللي هو قلنا عنه. So let's consider this. This is the spool of wire. هيدا السلندر اللي عم نحكي عنه. We know that there is a force exerted on the top of this cylinder, tangent على cylinder. What are the other forces acting on this cylinder? So basically we have مثل ما بتعرفوا we have the mg, the weight of this cylinder, and we have on the other side also the normal force that is exerted by the surface on the cylinder. So those are the three forces basically which are acting. Now, let's forget for a moment that there is a friction, and let's make the discussion based on these three forces. طيب أول شيء في عنا الفورس الF الN G والN, both they are on the vertical. ونحن بنعرف إنه ما في motion along the vertical. يعني if we apply Newton's second law حيطلع معنا sum FFy equals MAY equals to 0, and so we'll end up that N is equal to M times G. So هاي اثنين force بيعملوا balance, they counterbalance each other, and so that the cylinder remains at rest in the vertical direction. يعني it's all the time in equilibrium in the vertical direction. So هدول اثنين forces ما عم يعملوا ولا أي motion، ما عم بيأثروا على الموشن للأوبجكت. فلهالسبب رح الغيهم، رح شيلهم بس من الفيجر اللي عندي لحتى سهل على حالي بس الشغل. Now بقي عنا بس الفورس اف اللي ممكن تعمل موشن لهالاوبجكت. بس كيف ممكن تعمل له موشن؟ مثل ما نكون شايفين الفورس اف is at a given distance from the center of mass. So هالفورس مبدئيا ممكن تعمل rotation because the torque of this force is different than zero because it is at distance r from the center of mass. So كيف هي التورك لهالفورس F؟ Actually إذا بتشوفوا ترسموا الفيكتور V للpoint of application of the force F from the axis of rotation اللي هو center of mass، هيطلع معنا إنه التورك هي pointing inward. يعني التاو للF هي لجوا، معناتها إنه الأوبجكت حيبرم بهالشكل هيدا، حيبرم clockwise. وإذا كان حيبرم clockwise معناتها بنطلع نحن على النقطة التحتانية. نحن شفنا إنه قد إيه أهمية point of contact in the case of rolling motion and rolling without slipping بالتحديد. فما إنه حيبرم بهالشكل يعني هالنقطة هيدي حتكون عم تمشي بهالاتجاه هيدا. And this point will be moving with this with a velocity v in this direction اللي هي r multiplied by omega. هي equal السبيد تبع هالنقطة هي equal ل distance from the center of mass اللي هي radius لأنه موجودة على الطرف multiplied by the angular speed اللي هي omega. So we know that this is the acceleration. This is the way this point will be moving in case F is causing a rotation. بس كمان F it could cause a translation. بنفس المنطق يعني هل point B under the action of force F it could actually have a velocity due to the translation under the action of the force F. And so the point is this point أي وحدة at rest أولاً هل هي حتوقف؟ إذا وقفت معناتها لازم تكون الفي جاية من الترانسليشن قد الفي جاية من الروتيشن، ولحتى نعرف نحن بأي اتجاه لازم نشوف أي وحدة حتغلب على هالنقطة، هل حتغلب الترانسليشن أو هل حتغلب الروتيشن. فلهالسبب رح نعمل comparison ما بين الأكسلريشن due to the rotational motion والأكسلريشن اللي due to the translational motion، اثنيناتهم بسبب الفورس F، واللي بيغلب ساعتها حنشوف مين هو اللي رح يغلب أولاً وبعدين الفورس of friction حتوقف مع مين. So let's make this discussion. So من translation شو في عنه؟ من translation نحن بنعرف إنه ال F is equal to MA، يعني the acceleration acceleration اللي جاية من ال translation هي حتكون equal لل F over M. Voilà. So we can write down the acceleration of the translational motion is equal to F over M. بالنسبة للروتيشن شو بنعرف نحن بالنسبة للروتيشن نيوتنز سكند لو؟ بنعرف إنه tau of f is equal to I alpha, right؟ معناتها شو هي التاو للf؟ هي f multiplied by the radius لأنه الf موجودة على بعد r من الأكسس of rotation هي I alpha. And so we can deduce that I is equal to f times I r over I. طيب now the question is نحن ما نعرف مين حيغلب على النقطة P. هل حتغلب الترانسليشن أو حتغلب الروتيشن. So this is why we need to compare A to alpha. Right؟ لحتى نعمل comparison مظبوطة لازم نضرب الألفا بالآر لأنه الألفا it's an angular speed. لحتى نعمل لها comparison ب linear acceleration المفروض تكون مضروبة ب radius. So we end up with ال A هي F over M وال R times alpha حتطلع معنا F times R squared over I. مظبوط معناتها هون بيطلع ال F and F they cancel out بالنيوميريتور and denominator وبيبقى عندنا I divided by MR squared. So لحتى نعرف مين حيغلب لازم نشوف شو هو ال I اللي علينا. بما انه نحن هون we are dealing with a cylinder so that means that we have a I is equal to half MR squared. So we end up with half MR squared على MR squared مع انه هيك بيطلع معنا 1 over 2. شو معناتها هيدا الشيء؟ معناتها ان الاكسلريشن is equal to 1 over 2 so A acceleration coming from translation is equal to 1 over 2 times R alpha. So that means انه الروتيشن هي اللي حتغلب معناتها بهالحالة انه ال V is smaller than R omega وبالتالي هون ال vector velocity اللي هو جاي من الترانسليشن اوكي I'll draw it in blue الفيكتور في جاي من ترانسليشن هو عمليا اصغر من الار اوميجا فلهالسبب اذا حيكون في عندنا فريكشن هون لازم الفريكشن تلعب دور رئيسي واساسي اللي هو انه تخلي البوينت بي ات ريست تخليه motionless with respect to the surface لانه اذا كانت البوينت بي عم تعمل عم تمشي بنفس الوقت اللي الدولاب عم يبرم معناتها انه صار في عندنا rolling with slipping صار في عندنا slipping ونحن قلنا انه the object is rolling without slipping so if there is a friction force then it's gonna be a static friction force وهالstatic friction force حتكون بنفس اتجاه الاف يعني it should be to the right ليش؟ لانه لازم تدعم ال V اللي جايه من الترانسليشن لازم تكبرها لل V اللي جايه من الترانسليشن لحتى تصير قد ال V اللي جايه من الروتيشن بشكل انه البوينت P يبقى على طول at rest يبقى motionless with respect to the surface يعني ما في motion للبوينت P and in this case we have rolling without slipping. So this is it. هاي الدسكشن يلي مبدئيا لازم نعملها لحتى نوصل لنتيجة انه ال F is pointing to the right. Now once we have set all our forces وحطينا كل شيء now let's apply Newton's laws of motion. So we have a translation and we have a rotation. We are going to apply Newton's second law for translation and Newton's second law for rotation. And then from the equation, we are going to then determine the acceleration and the friction force. So the spool of wire is rolling without slipping. So we can apply Newton's second law. Let's start with the translational motion. So we have sum of external forces is equal to M times A. Sum of external forces is equal to M multiplied by A. إذا بنجي بنعمل projection للفورس F للفورس friction للacceleration. So we end up with F plus F equals to M multiplied by A. هي أول equation جاية من ال Newton's second law for translation. وبعدين إذا بنطبق Newton's second law for rotation كمان بيطلع معنا إن sum of tau of external forces is equal to I alpha. And now we have two torque that are acting. بالنسبة للF حطينا شو هي التاو اللي لها and let's actually now call it tau F. بقي نجيب شو هي التاو للفريكشن فورس. الفريكشن فورس هي applied just in an symmetric position with respect to F. كمان at a distance, so let's call this RF, at a distance radius from the axis of rotation. And actually, if you just use your right hand rule, you will find that tau for the friction, it is pointing in the opposite direction with respect to F. So it's pointing outward. يعني عمليا هي anti clockwise. So from here we can deduce that okay التاو f هناخد الدايركشن للالفا to be the positive direction. ما انه الالفا pointing inward فرح ناخد الانورد هي to be the correct او the positive direction. الالفا pointing inward فلازم يطلع معنا التاو للاف هي positive والتاو للفريكشن هي negative. So we end up with plus tau f minus tau of the friction is equal to plus I alpha. And so if we just replace كل تاو بقيمتها بيطلع معنا fr minus fr is equal to I times alpha. So هي تاني equation تطلع معنا من ال Newton's second law for rotational motion. Now if we replace ال I بقيمتها والألفا بقيمتها بيطلع معنا أول شيء ال I it's given by half mr squared لأن هون we have a uniform solid cylinder and the moment of inertia of a uniform solid cylinder with respect to its central axis يعني axis through its center of mass it's given by half mr squared. This is number one. And then for the alpha, we have to replace alpha by the acceleration of the center of mass divided by r. لأنه we have rolling without slipping, and we have seen in our course that for rolling without slipping, we have the condition that a center of mass is equal to r alpha. So alpha is equal to a center of mass over r. Let's just put here over center of mass as well. And so we end up with f minus f كلها multiplied by r is equal to this expression. Now if we simplify, if we just make some reduction one lil r and r on the other side, so we end up from the Newton's second law for rotation, we end up with f minus f equals to 1 over 2 m times a center of mass. And so this is the second equation that we have at the end. So let's call them equation number 1 and then equation number 2. مطلوب مننا نجيب بأول part كان بالبارت A how much is the acceleration of the center of mass. So the acceleration of the center of mass المطلوب مطلوب نجيبه as a function of F. So إذا بنعمل 1 plus 2 we will actually eliminate the friction force. So 1 plus 2 we end up with 2F is equal to 1 plus 1 half اللي هي 3 over 2 times m times a center of mass. And from here we can deduce that the acceleration of the center of mass is equal to 4f divided by 3m. 2 times 2 times f هي 4f divided by 3m, and this is what we have to show. فإذا طلع معنا أول جواب لأول سؤال. طيب خلينا نكمل بتاني سؤال. تاني سؤال كان مطلوب منا نجيب أو نبرهن إنه the magnitude of the friction force is equal to 1 over 3 times f. وكمان هنا قالوا لنا لازم تفرجونا انه الاف هي pointing to the right. يعني نحن عملنا analysis لحتى نقول ليش هي pointing to the right، بس هون لازم من الايكويشن نقدر نستنتج اذا هي pointing to the right or not. How؟ طيب اول شيء خلينا نقول انه نحن بدنا نستنتج شو هي الاف now, right? So we can write down then f as equal to من الايكويشن number 1 فينا نقول انه the friction force F is equal to m multiplied by a center of mass minus force F applied on the wheel on the spool of wire. So m multiplied by the center of mass هتطلع معنا 4f over 3. m and m they cancel out minus f, and 4f over 3 minus f is nothing else than 1 over 3f. So أول شيء طلع معنا من هون إنه الفاليو للf هي 1 over 3 times f اللي هو الشيء اللي كان لازم نبرهنه. وبما انه هون ما طلع عندنا نيجاتيف ساين بقلب الايكويشن، هذا الشيء بيعني انه the direction of the friction force that was chosen in our figure is correct. لو كانت هيدي الدايركشن اللي نحن حطيناها للفريكشن فورس منا صحيحه كان لازم يطلع معنا نيجاتيف ساين بهيدي الانسر اللي طلع معنا بالاخير هون. لو بهالايكويشن طلع معنا نيجاتيف ساين ونحن اخذينها to the left ساعتها بنقول انه the minus sign indicates or it means that the friction force it points to the right and not to the left as it was taken in our case. So نحن هون بس بما انه نحن اخذناها اصلا من الاساس مضبوطه to the right وشرحنا ليش اخذناها to the right طلع معنا جواب positive ما في ولا اي negative sign. So this is it for this question. Now we have still the last part, we have to determine the speed of the center of mass of this spool after it has rolled through a distance d. فإذا بعد ما يكون مشي a given distance d, let's just draw a small figure in here. إذا كان originally بهالposition, okay, and then it has rolled through a given distance بوقت ما بعد ما مشي distance d صار بهيدي الposition, and the distance between the center of mass position from the initial to the final time, it's given by d. هيدي الديستنس اللي مشيها center of mass هي عبارة عن d. So المطلوب مننا نجيب شو هي the speed of the center of mass in this case when it reaches this final position. Okay, let's have a look at the acceleration. The acceleration is equal to 4 multiplied by f over 3m. And we know that the force F acting on this object is constant. هو قال لي بالgiven it is unwound under a constant force F, which means that the acceleration is constant. And if the acceleration of the center of mass is constant, then we can use the kinematic equation, which is given by v squared minus v0 squared is equal to 2 times a times x minus x0. هون الديسبيسمنت عم بيصير on the horizontal axis, فلهالسبب استخدمنا delta x instead of delta y. Now we know that v0 squared is equal to 0 because in the given it was said that this object was at rest initially. It starts from rest, and we know that x minus x0 it's nothing else than the distance d. So if we replace نحط كل شيء بقيمته بيطلع معنا انه v squared is equal to 2 multiplied by الاكسلريشن حسب ما جبناها قبل هي عبارة عن 4f over 3m, and this multiplied by the distance d. So we end up with v squared equals 8f times d divided by 3m. And so we end up with the velocity v of the center of mass is nothing else than square root of 8fd over 3m. هو ما قالنا شو قيمتها للv center of mass، بس هيدي هي اللي طلعت معنا الجواب. Yeah, this is it for this problem. Of course, in the last part, you can also use the principle of conservation of mechanical energy from the initial position to the final position to show that the speed of the center of mass is given by this expression as well. So chapter 10, problem 77. A string is wound around a uniform disk of radius r and mass m. The disk is released from rest with the string vertical and its top end tied to a fixed bar, as shown in this figure below. So here's the disk, and here is the string that is wound around it. So we have to show that the tension in the string is 1/3 of the weight of the disk in part A. In part B, we have to show that the magnitude of the acceleration of the center of mass is given by 2 times g over 3. And finally, we have to show that the speed of the center of mass is given by square root of 4gh over 3 after the disk has descended through a distance h. Finally, verify your answer to C using the energy approach. So obviously, we cannot use the energy approach for the first 3 parts. And this is kind of normal because using the energy approach, we don't have access to the forces. So we cannot show that the tension, for example, is 1/3 to the weight of the disk. To do so, we have to apply Newton's second law. So this is why. Let's go on and let's solve this problem. So here is our figure. So this is the disk here, and you have so it's actually attached to some support sailing through the string which is wound around it. Now, in the first question, we were asked actually to show that the tension in the string is equal to 1/3 times mg. So for this reason, we are going to apply Newton's second law. And then let's first define what are the forces that are acting on this disk. So as you know, we of course have the weight. We have the force applied by the Earth on the object, which is given by m times g, the gravitational force. And we have at the same time, of course, the tension in the string. So here is the tension. Okay, so here is the tension in the string, which is given by T. So this is it. Now let's apply Newton's second law. In order to apply Newton's second law, we have first to define the type of motion that we are studying. So this disk, as you can see, we have a string that is wound around it. When it is released from rest, actually الخيط رح يفك عنه، وبالتالي شو حيصير فيه لهيدا الاوبجكت؟ هالديسك رح يبرم in the direction اللي هي clockwise بهالحالة. Okay, let me just draw it. So it will rotate around the axis passing through its center of mass in the middle. At the same time بنفس الوقت بيكون عم ينزل، لأنه بمكان ما بعدين هو قالنا إنه بصير in this position اللي هي after it has descended a distance h, which means that the center of mass, it has traveled from a given position up there to the final position in here. إذا اعتبرنا أنه السنتر للديسك هو its center of mass. So that means that this disk is not only rotating, but it is rolling. It's undergoing a rolling motion. And so it's a combination plus translation. This is why we are going to consider Newton's second law in both versions, for the translation and for the rotation. So let's write this down. Disk, it undergoes, actually, the disk undergoes a rolling motion and again here it's a rolling motion. That means it's a translation plus rotation. So this is why we are going to apply Newton's second law for both translation and for the rotation. So let's start by the translation first. And so let's write down sum of external forces is equal to m times a, right? So we have two forces basically acting on this object, T will mg, and the object is moving down, so the acceleration is in the same direction as mg. So we can actually, instead of that, we can write down sum of fy is equal to m times ay, لحتى نقول إنه the motion is only along the vertical axis. So we end up with minus t plus mg is equal to, or here the mass is capital M استعملت. So it's ma y, and so it's m multiplied by a. So this is the first equation that we get from the Newton's second law for translation of the center of mass. Now we move on, and then let's apply the Newton's second law for rotation, which is given by sum of external torques is equal to I times alpha. And so we have to consider both forces acting in this case. So we have tau T for the tension plus tau G for the gravitational force to be equal to I multiplied by alpha. But as we know again that since mg, it passes through the axis through the center of mass, then this it produces zero torque. It does not contribute to the rotation motion, and only the tension is contributing. So to draw the torque for the tension, we have first to specify the position of the point of application of this force. So the point of application of this force is obviously here on the rim of the disk, and so the vector r would be in this case like that. So here is the vector r. It's nothing else than the radius of the disk. And since the tension is tangent to the circular يعني object اللي هو بهالحالة disk, then we know that the tangent and the disk, they are perpendicular, وبالتالي r is perpendicular to t. Now, if we use our right-hand rule, we'll find out that the torque of the force tension, it's pointing inward. So tau, it's pointing inward. أو بمعنى آخر هي clockwise، مثل حركة الدوران اللي عم بتصير اللي هي ممثلة بالألفا. لأنه كمان الألفا, if you consider the rotational motion of this disk, also using our right-hand rule, we'll find that also alpha is pointing inwards. كمان الألفا هي لجوا. And so let's just make the projection in here. So we end up with tau for the tension, هي عبارة عن tension T multiplied by the distance between the point of application of the force T and the center of mass of the disk اللي هي nothing else than the radius. So it's T multiplied by R is equal to I times alpha. Right. So هاي تاني equation طلعت معنا اللي هي كمان فيها. So هون في عنا two equations with three unknown basically. عنا التنشن، عنا ال A وعنا الألفا. So it's not going to work like that. We have to make some simplifications. So أول شيء, let's write down what is the value of I. Actually, if we have a disk that is rotating through its center of mass, هون ما تنسوا نحن عم نشتغل على center of mass. هذا هو ال axis of rotation. So هون ال I اللي عم نحكي عنها هي I center of mass. And the moment of inertia of a disk with respect to an axis through its center of mass, it's given by 1/2 multiplied by m times r squared. Okay, so this we can find it in our table. And here we have rolling, and we have rolling without slipping. And so we can actually use the condition for rolling without slipping that is given by A center of mass is equal to R times alpha. This is why alpha is equal to A center of mass divided by R. So احنا ال A center of mass سميناها، خلينا نسميها A center of mass بس خلينا يكون نفس ال nomination everywhere. And so we can write down finally بيطلع معنا هون TR is equal to this expression. إذا بنجي بنعمل شوية بس بنختزل بعض ال parameters. So we end up with R هون، ال R من هون بتطير، كمان ال R من هون وال R من هون. And so we end up with T equals to 1/2 times M multiplied by A times the times A of the center of mass. So هي بتطلع معنا تاني equation من Newton's second law for rotation. So we have two equations with two unknown, tension will acceleration of the center of mass. In part A, we are looking for the tension. So we have to eliminate the acceleration of the center of mass. And so we end up with minus T plus M times G is equal to the mass multiplied by acceleration center of mass. From the equation 2, we can write down A center of mass is equal to 2T over M, which is nothing else than 2 times T. So as I'm going minus T from the right-hand side to the left-hand side of the equation, we end up with 3T equals M times G. And of course, from here we deduce that the that the tension is 1/3 times mg. And so finally T is mg over 3. So I can build part A. Now with part B, we were asked to determine or to show that the acceleration of the center of mass is 2/3 times g. So we can very easily now deduce the acceleration of the center of mass. It's given by 2 times t over m. So it is equal to 2 over m multiplied by mg over 3. We reduce the mass factor from the numerator and the denominator, and so we end up with 2g over 3. And so this is what we needed to show, اللي هي إنه acceleration of the center of mass is given by 2g over 3. So this is it. هول two solutions برهناهن. In part C, we were requested actually to show that the speed of the center of mass of this disk is given by square root of 4gh over 3 after the disk has descended through a distance h. So we have to show that the speed of the center of mass بهالposition هيدي تحت بعد ما الديسك نزل distance h هي equal to square root of 4gh over 3. So we have now two times, basically two moments. The initial time when the disk was at rest, so it was released from rest, and with v initial equal to 0, and some final time where we have to determine its speed, v center of mass. And we know that delta y between the two positions is given by h. So this reminds us the very famous equation اللي بنستعملها بشكل مفرط كنا اللي هي بتقلنا انه v squared minus v0 squared equals 2a times delta y. But we have first to check that the acceleration of the center of mass is constant. But here it is the case. We have a constant acceleration is equal to 2g over 3, which is a constant. Then we can apply the relation v squared minus v0 squared equals 2a times delta y. So y minus y0 لأنه عم نحكي عن vertical نحكي عن vertical motion. So displacement is vertical. V0 is equal to 0 لأنه it was initially at rest. We know what is V final. It's the one that we are looking at. هي ال V squared هي ال V اللي عم ندور عليها. V center of mass is equal to 2 times ال A هي equal ل 2G over 3. هيدي هي ال A center of mass of the object. And delta Y هي nothing else than H. So finally, this is nothing else than 4GH over 3. And so from here, we can deduce that the speed of the center of mass of the disk after the disk has descended a distance H is given by square root of 4GH over 3. And so this is how we can show it. So this is it for the parts A, B, and C. Now what we are requested to do is we are actually requested to show that we can show and determine the center of mass of the disk to be equal to square root of 4GH over 3 after the disk has descended through a distance h, but not using the kinematic equations, but instead using the energy approach. يعني using the conservation of energy. So in part D, using the energy approach, we are in the case of rolling without slipping, as we have said in part A. Since we have rolling without slipping, that we have conservation of mechanical energy. So if you apply the principle of conservation of mechanical energy, of mechanical energy, we can write down then mechanical energy at time t initial is equal to the mechanical energy at time t final, where time t initial and time t final, they are defined by the initial position of the disk when it was released from rest, and the final position or the final moment is defined by the time when the disk was at distance h from its initial position downward. So we can write down then K initial plus U initial is equal to K final plus U final. Now, the disk, first of all, it was released from rest, so K initial is equal to 0. And if we take the downward position to be the position for the gravitational potential energy, so I will just draw here a small figure. So احنا أخذنا هيدا هو الديسك in initial position, okay? وقلنا إنه هو موجود على هالنقطة كان ال center of mass. And let's suppose إنه رجع هو نزل. It has descended a given distance h as we are discussing in the given. So such that the distance between the center of mass and the initial position or final position is given by h. Okay. So if we take this final position to be our reference level for the gravitational potential energy, okay, then we can write down that U final is as well equal to 0. And so we can write down finally that for the initial state, the gravitational potential energy is given by m times g times h is equal to the final position. We had kinetic energy for rolling motion. So we have both kinetic energy for the translation part and kinetic energy for the rotation part. So we had half mv center of mass squared plus half I center of mass times omega squared, right? So this can be written as we have فإذا نقدر نكتبها بهالشكل فإذا m times g times h is equal to 1 over 2 times m v center of mass. v center of mass هي our unknown plus half the moment of inertia of a disk with respect to the axis through its center of mass, as we have used earlier, here half times m times r squared, where m is the mass of the disk and r is its radius multiplied by omega squared. But actually, since we are in the case of rolling without slipping, and the condition for rolling without slipping is given by v center of mass equals to r times omega. So we can here replace 1 over 4 times m. We can replace r squared omega squared with v center of mass squared. هون بهيدي الاكسبريشن الار سكويرد مع الاوميجا سكويرد حطيناها v center of mass لانه this is the condition for rolling without slipping. And so we end up with mgh is equal to this whole expression. Now نختزل الm everywhere بيطلع معنا انه gh is equal to 1 over 2 plus 1 over 4. It's 3 over 4 times v center of mass squared. And so we can deduce finally that V center of mass squared هي 4GH over 3 وإذا بنشيل squared بصير في عنا square root of 4GH over 3. And so this is what we need to show. We need to show that the speed of the center of mass of the disk is given by square root 4GH over 3 using both Newton's second law and the kinematic equation approach and using the energy approach.